Okay, pause and copy this, pause and copy, pause and copy. Okay, some logic here. Just underlining point 2 from above. Maybe I'll expand over here. So we're saying that if limit of an is non-zero, that implies that the corresponding series is divergent. So it's kind of like saying Jordan is in Hertzberg Hall. This implies that Jordan is at John Abbott College. But if I say Jordan is not at Jack, okay, if I take the opposite of this statement, what happens is this arrow gets reversed. If I look at the negation of this statement. But if I have this implication, okay, it does not imply that the other direction is true. So if I'm not in Hertzberg, does that imply that I'm not at John Abbott? The answer is obviously no. So I'm going to cross out that arrow. Okay, all this stuff in red is to explain my reasoning here. Okay, the moral of the story, the take-home bit of information is this one right here. Okay, if your limit is 0, it does not tell you anything. It does not tell you. It does not tell you that this series is convergent. And here's an example to show you why. So pause and copy all this. So we have our original series, corresponding sequence. Obviously, the limit here is 0. Okay, the denominator is growing, the numerator is not, so limit 0. Now, I'm going to show you that this series here actually diverges, even though this limit is 0. Okay, so I do a clever little trick here. What I'm going to do is look at some partial sums. Let's look at S4 and these two terms in particular. If I replace this third with a quarter, what happens? Well, I get something small. Oops, I get something. This is going in the wrong direction. I get something smaller. So change that, change that inequality. So if I replace a third with a quarter, I get something smaller over here. Okay, and what is this equal to? This is 1 plus a half plus a half, which is equal to 1 plus, I'm going to write it as 2 over 2. And you'll see why in a moment. Now looking at S8. I'm going to replace this with a quarter. And I'm going to replace these three terms with 1 over 8. And I'm going to obtain something smaller. So this is a half, and this is a half. So I get 1 plus 3 over 2. Now look at the pattern that's emerging. S2 is 1 plus 1 over 2. S4 is 1 plus 2 over 2. S8 is 1 plus 3 over 2. So let's write that as S8, which is S2 to the power of 3 is 1 plus 3 over 2. Oops, is bigger than. S4, which is S2 squared, is bigger than 1 plus 2 over 2. So if I look at the next logical thing to try, it's actually S16, which is S2 to the power of 4 is bigger than or equal to 1 plus 4 over 2. And in general, if you have S2 to the power of, let's say, n, is bigger than or equal to 1 plus n over 2. Therefore, the limit as n goes to infinity of Sn is infinite, right? Because this quantity here is at least something that is growing. See, this is growing without bound. And what do I get from this? It tells me that summation 1 over n is divergent. Okay, because the sequence of partial sums has a limit equal to infinity. Okay, that's a little trick here. A little tricky proof here. You won't be expected to reproduce this, but just want to convince you that just because the limit of an is 0, it doesn't mean that the corresponding series is convergent. Okay, pause and copy theorem 6 here. Now, we just looked at p is equal to 1. And now we have information about all values of p. So we actually need p to be bigger than 1, strictly bigger than 1. In fact, as soon as you are bigger than 1, as soon as p is bigger than 1, this guy starts to converge. So as an example, just smush in here. Summation 1 over n to the 1.00001 is convergent. Summation if P is below 1, you get divergence. Okay, so nice theorem that summarizes what's happening for series of this form. So, oops, let's pause and copy this now. Now, what we're going to do is use our theorem 6. Okay, we have to determine P. If it's bigger than 1, then we have convergence. Otherwise, we have divergence. A, P is equal to a half. So P is less than 1. Therefore, summation 1, oops. Summation 1 over root n is divergent. Okay, it's as simple as that. You just notice that this is n to the 1/2. So P is a half. P is less than 1. So we have divergence. B, P is 5 over 4. So P is bigger than 1 in this case. So the summation is divergent. Whoopsie daisy. Screwed that up. P is bigger than 1. Okay, so we have convergence if P is bigger than 1. So I screwed that up. I was thinking about C when I was doing B. So this is convergent. C, I'm going to break it up. I get 1 over n plus 1 over n to the 3/2. Now what's happening here? We have two different p-values. This p-value suggests convergence, but the p-value of 1, which is here, suggests divergence. And overall, we're going to have divergence, okay, right? Because well, the reasoning is that this series can't possibly converge because, well, more or less, roughly speaking, it is bigger than this series rectangled here. And this series rectangled here is divergent, so plus infinity. Anyways. So I'll write it like this. Put a little star here. Summation 1 over n is divergent. So the original series is divergent too. Okay, a couple things there. To be a little bit careful. Okay, my reasoning again was that this rectangled series is divergent plus infinity. So the larger series must be divergent.